Hey everyone, this is my N-body simulation project, which is all about simulating bodies in space affecting each other with gravitation. So the first thing that you see upon loading the page is this scenario. So we have some pre-made scenarios, and this one is elliptical orbits. So you can see there's a body here orbiting an elliptical orbit, and there's also one that orbits much farther, and right on time it comes back around. So you can see that there's some vectors. So you have what's on screen. So we can pause it right here uh, to take a closer look, or we can also like step frame by frame, tick by tick, to sort of go in a more precise way and see everything more precisely. So we can see that the blue vector is the acceleration vector. So that's kind of pointing in the direction of the force on the body, and that's you can see that it's pulling it in toward this very massive body here, which is like a star. And then the red vector is like the velocity, that is the velocity, and you can see that it's mostly tangential, but it's also a little bit out because this body in the elliptical case is kind of, it's getting farther away. So there's some tangential velocity and also a little bit radial out as it gets farther away. And then when it's at its farthest away, it's tangential and a little bit radial in. You can also control the camera to zoom in or out if you want to follow the full orbital path of this body right here. But this is really simulating in real time with by calculating the acceleration according to the law of universal gravitation, Newton's law, and then turning that into the acceleration, and then using Euler's method to take small steps and calculate the velocity and position at each step by changing them slightly using the derivatives. But anyways, enough of that math stuff. What else is there? So you have options to draw, of course. So there's a lot of other scenarios, and we'll get into those. And also, like, you can add all your own objects if you don't want to use the pre-made scenarios. But those are just some interesting scenarios. So there's the path trace, of course. So we can turn that off. And once you turn it, and that deletes the history. So when you turn it back on, it'll start drawing from where the body is again. There's the velocity vector. So that's the red. We can turn that off. And the blue. Sometimes that's useful if you have a ton of bodies and the screen is getting cluttered. There's also an option to show crosshairs, which is just the center of the screen, which helps you when you're zooming in or out. There's debug info, which is really useful because that allows you to see, so I'll turn this all off, the mass, position, velocity, and acceleration of every body. So for the vectors, which is the position, velocity, and acceleration, you first see the x and y component, and then the magnitude is in parentheses. And you can see that in case you were curious, when we have the velocity and acceleration vectors on, it doesn't look like there's any velocity or acceleration for this really big body here because it's so massive, right? Because according to the law, it's technically equal force, right? That according to the law on this body and this body, but there's a much smaller acceleration on the big, more massive body according to Newton's second law, which is that the net force equals the mass times the acceleration. Because the mass is so much for the really big, massive, this big body in the center here, the star, the acceleration really isn't much. But here's another cool feature for the camera. If you left click on a body, it'll highlight yellow and it will be focused on it, so we can follow it around. So WASD, don't do anything anymore, and you can just zoom in or out. So that's useful for following the orbiting bodies. And then click on it again, and we'll be back in like free camera mode. But if we center on the big star and zoom like all the way in, we can start to see that there's some really small acceleration and acceleration and velocity vectors. And we can click that button to reset the camera. And if we look at the debug info, it'll show us that the velocity and acceleration vectors are there, but they're just so small, right? This is in thousands, right? So that's really, really small, times 10 to the 3, because every pixel on the default zoom level is a million meters. So, and you can see the velocity and acceleration of these are, times 10 to the 7. That's in the 10 millions. These are only in the thousands. So it makes sense that you're not able to see it, and it doesn't really look like it's moving at all. You can also, of course, add your own bodies because this is like a real-time simulation. It's not just a recorded thing. So let's see if we can get the body to orbit. No. Well, Yes, but it's really elliptical. So another thing is that there's no collision. These are really just point masses, and the visuals of drawing it as a large circle is really just to kind of show the mass. There's no collision, so there's no reason really in the simulation that the sizes don't actually affect each other. What else can we do? So we can right click to delete a body, and you can think about it. What do you predict will happen to these smaller bodies when we delete the big central star? Well, they just kind of fly off in a straight line. And that's because there's nothing to keep them in anymore. The centripetal force there, keeping them in orbit, is not there anymore. And technically they affect each other with gravity, but it's just such a small force. If we put the debug info back on, we can see that the acceleration is almost nothing, 3.15 meters per second squared, compared to the velocity that already exists, which is in the tens of millions, right? That's like 35 million meters per second. So the acceleration really isn't going to do much at all to change that velocity, just because these bodies are just so, there's barely any mass, so they really don't affect each other much. So that's how you can add a body. We showed how you can delete a body. We'll see later you can also add a body more precisely with this form on the right here. You can enter precise numbers. But for now, we'll leave that to the end because we're going to do some math to get a circular orbit. And for now, we'll just go through the other scenarios. So this is a pretty cool one. This is resonant orbits, which means that resonance means that there's an integer relationship between the periods of the orbits, which means, so I'll call these bodies A, B, and C from inner to outer radius. And you can see if you follow these, A and B, that they have a 1 to 2 ratio in terms of their orbits, their periods, which means for every 2 orbits the inner one does, body B will do just 1 orbit. So you can see that they're synced up here, and then body A does another full orbit, and then on its second, they'll sync up again. And the frame rate's a little low just because I'm recording. It's not really this low when I use it normally. Then A and C have a 1 to 4 ratio if you watch. So body A will do 4 orbits for every 1 orbit body C does. And then of course, B and C have a 2 to 1 ratio, but it actually syncs up on the left side if we watch just a little bit more to see when they sync up here. So for every 2 rotations body B does, body C will do just 1. In general, the farther you move out, the longer the period will be. So let's go through all the other scenarios now. So clear all bodies with that button. And this one's my favorite probably. We have a binary star system. So that means that we have 2 stars orbiting each other. I call them stars. These are all really just point masses, but we'll call the more massive bodies the stars. So, and they're kind of orbiting each other because they're equal mass and they have their initial velocity, so they're kind of just orbiting the center of mass between them here. But we also have a very small body, a planet, orbiting one of the stars individually. And so this is a real analog to real star systems, because we also have this planet out here orbiting kind of both of them together, right? So, and this is a real analog, if we look here, to an S-type orbit and a P-type orbit. So, or they're also called non-circumbinary and circumbinary. And one interesting thing about these types of orbits is that they're not really guaranteed to be stable. So for example, for non-circumbinary planets, if a planet's distance exceeds about 1/5 of the closest approach to the other star, orbital stability is not guaranteed, which basically means this inner planet with the S-type orbit cannot really get too close to the other star, right? If it had a larger radius around this star that it's orbiting around, I'll turn off the path trace, that might help with the frame rate, then it would start to become influenced too much by the other star's gravity, and it would probably get kind of thrown out of orbit. It wouldn't really be stable. It might get transferred to another orbit. And then, in contrast, this P-type orbit, its orbit must be farther away. So orbital stability is guaranteed only if the planet's distance from the stars is significantly greater than the star-to-star distance. And it says later about 2 to 4 times the binary star separation. So basically, that means if we were to make this orbit closer, if it were orbited closer inside, the difference in orientation, right? Because these stars are constantly changing and they're both orbiting each other. That would start to affect the planet. The planet would because it experiences different forces of gravity actually, depending on the orientation of the planets, or sorry, the stars, and so its orbit wouldn't be as stable and circular like it is out here. Because the farther away it gets from these two stars on the inside, the more the stars kind of just become the center of mass on the inside, and the orientation starts mattering less, and it becomes more like a constant. You can treat it almost like if you were to sum up their masses and place it in the center, it would be similar to that. More similar to that, the farther you get away from the system. But aside from all that kind of more physics-based stuff, it's also just creates cool patterns to look at. I really like the S-type pattern here. Next one, 4-star system. This one's pretty simple. They just orbit in a stable circle. And I think if you watch long enough, which I won't do because we don't have all the time, but you can visit the website at this URL, which will be in the description, and play around with it yourself. I think they might eventually, knock themselves out of orbit. It's not 100% stable. But this one's pretty simple, so not much to say. They just orbit each other in a circle, but it's pretty cool to look at. And maybe, let's see if we can knock them out of orbit. So you can just click once to add position, click another time to add the mass, and then click one more time to add the velocity. And that will kind of screw with them. So that's pretty cool, and you can kind of see them go off. And when they get really close to each other, the acceleration vectors kind of go crazy because there's so much force on them. So that's why it's sometimes nice to turn it off. But sometimes it's also maybe you want to see it. And it creates these really cool traces because it's so kind of chaotic. Next one, moon orbit. So this was my attempt at adding a star with a planet orbiting circularly around it, and then trying to get its own satellite, a moon, orbiting around the planet. I wasn't able to get 100% perfect, so it's not really a stable moon orbit, and it's also not. It also clips into the planet. It intersects with the planet. One thing that I kind of forgot to mention about when we were talking about the the values, like how many, the fact that, so in the debug info, I'm going to delete the moon actually so we can see the debug info. The position, velocity, acceleration, these are all like SI units, right? So like meters per second, and meters per second squared. But a few things that make it a little not realistic is that it's at a 5 times time scale, and so that's just to make it so that the periods are a lot lower, like smaller, so that we can see the orbits. It's just more interesting to watch when the periods aren't super long. And then the other thing is also the planets. These radiuses or radii, given the masses, pretty much all the bodies are much denser than they would be in real life. I'm pretty sure, and that's just because that density allows you to get more massive bodies closer together. And again, that's just to make the periods much faster. Because in real life, periods are typically a little longer, at least a few days. The Earth's period around the sun is, a year, of course. And so we want periods in seconds, not days or weeks. And so you want dense bodies really close to each other. But you can still do the math. If you were to take, the masses and the radiuses, you would be able to calculate the period, with the velocity. But then you have to multiply that by 5, or technically divide it by 5 for period, because it's also at a 5 times time scale. Anyways, moving on. And then the last scenario is just a bunch of random bodies. So they kind of just influence each other and kind of, dance around. But one interesting thing about this is that maybe you've noticed, but I've been clearing all bodies going in between scenarios. And that's because when you add a scenario, it doesn't clear the other ones. So we could add the elliptical orbits here. And now that we have this really massive body in the center, that will start to influence all these random smaller bodies. And we'll turn off the acceleration because it gets so crazy. Because there's no collision, the smaller bodies can't actually die or get absorbed or get destroyed on the really big star. So they have no choice but to just get flung out really far. And so you can kind of see them coming off. And so it's pretty cool to watch. And if we add the path traces, you can see them all kind of pointing radially inward toward the center where it's all coming from. And also sometimes you get some orbits maybe. I think maybe this one is orbiting elliptically. Looks like it's going to come back in. Yeah, it looks like it's in some sort of elliptical orbit. But also they get so close to the central body that they'll start influencing it and kind of pushing it around. Anyways, that's enough of that. So the last thing we'll do is use this form of adding a body to add a body really precisely using some math to get a circular orbit. So if we add a central body, so that's I'm using E for scientific notation, so 10 to the 33 kilograms. Let's say we want a smaller body, so E29. That's let's just choose some radius times 10 to the 8 away, right? But if we just add it like that, it's just going to fall toward the body. Oh, I'm not showing velocity and acceleration. It's just going to get pulled toward the body and get flung out the other side because there's no collision. So we need some initial velocity, of course, either down or up to get it, tangentially, to get it to orbit around. But we also need a pretty precise velocity if we want a circular orbit, because if it's too much, it could, escape completely if it's really too much. And if it's a little too much, it'll orbit elliptically. It'll go too far out on the other side and come back in. And if it's too little, it might get, flung around and escape that way. Or it could just be elliptical again, but closer on the other side. So if we want it circular, we'll have to use some math. So I'm not going to walk through step by step. Maybe I could if anyone's interested in that. But you just essentially use Newton's second law of net force equals mass times the acceleration. And then the only force on the body we add out here is going to be the force of gravity, g m1 m2 and over r squared. And then you use the fact that in circular motion, the centripetal acceleration is equal to the velocity v squared over r. And because it's circular motion, we only have centripetal acceleration. There's no tangential acceleration. Essentially, that means the only component of acceleration is inward toward the center, of the circle. It's not accelerating along any tangential component. So if we combine those and do some substitution, you'll come out with the when you solve for v, the velocity, you'll find that a velocity for circular motion under gravity is equal to the square root of gm over r, where this big M, capital M, is the mass of the central body, or the star. So one thing of note that maybe surprises people is that the mass of the orbiting body, like the planet, is actually not in this formula at all. And so that implies that it really doesn't matter, right? Whatever the mass of the planet is, it'll still be in orbit. And we'll see there is kind of one caveat to that pretty soon. But that makes sense, right? And I'll show it off that it works in the simulation. So g is just the gravitational constant, 6.67 times 10 to the negative 11, which is the real value and also what I'm using in the simulation. The mass we've already set for our star is 10 to the 33, and the radius is 10 to the 8. And so that calculation gives us this value, which we can just copy paste for the velocity. So we'll copy paste that in and add it and play it. And that looks pretty circular. We can use the debug info actually. And if we look at the position, then this magnitude of position there in the parentheses, that gives us the distance from the origin. And you can see that it's pretty much, it changes a little, but it's still pretty good, pretty circular. And we can also show that if we add bodies of different masses, that it'll have the same orbit. And so the one caveat to that I mentioned before is that the mass of the orbiting body does, even though it's not in the formula, it is possible, of course, for it to affect the orbit, because this formula assumes that the mass is negligible. The mass of the orbiting body isn't going to affect the central body, and the central body is just going to stay stationary. So if we increase the mass enough, let's say it's like 10 to the 31, and we add that body, then that's going to start to pull the star out of position. because it's no longer a negligible mass. And it'll start to kind of make an unstable orbit, because you can see it's starting to move that central star. And so it kind of breaks down. So the mass doesn't matter as long as it's small, right? The mass of the orbiting body, as long as the mass is negligible compared to the mass of the central star, the central body that it is orbiting around, then it doesn't matter. But if it starts to affect it and pull the central star out of position, then it does matter, of course. So we can clear them all. And the last thing I'll show is what I was saying before about that if the velocity was too high or too low, so again, that's the circular one, but if we made it a bit too high, we would get, or too low, we would get the elliptic orbits I was saying before. And hopefully, we'll be able to see a kind of cool interaction where these bodies will kind of knock each other out of orbit. Right there. That's what I was going for. Perfect. So you can see one got knocked into a much lower orbit, and one got knocked into a much higher orbit. So I think that's pretty cool. So that's the n-body simulation. When you use the project, there's a bunch of information above that I just kind of talked through. But I really enjoyed making the project. I hope you enjoyed watching this video. Maybe you learned a little bit of something. I definitely learned a little bit. I always enjoy, I like physics, I like programming, so I like making a project where they combine. I made a project similar to this in that it's also related to physics and motion. My double pendulum simulator, which I also have a video on, and that's very similar because I use a closed form formula for the accelerations and then just use Euler's method to numerically integrate for the velocities and the positions. But anyways, that's it.